if it helps. So today we're actually done with the hardware part of this course, or the first module called hardware, and we'll move on to now some kind of general efficiency techniques, which are very relevant to hardware, but do not necessarily speak to the design of hardware itself, rather the efficiency of neural networks. So the first thing we'll talk about is quantization. Yes, James. It's always posted right after the class. Do you like to follow kind of while the lecture is going? Is that okay? The thing is, there are these questions that I ask throughout the lecture, and then the answer is right afterwards. So that's one reason to post it after the the lecture. So okay, so if you haven't already taken one of those TinyML kits, come to my office to get one. My office is 257. So you need that for next week when assignment 2 is released. Yeah, I already asked how's A1 going. If you do have any questions, just drop by my office or send me an email. I'm usually in my office, huddle, I mean. And then I'm going to prepare a few slides about the term paper and the presentation next week as well, because I've gotten a few questions about that. But yeah, so you'll know more about it next week. So this is kind of the overview of our course. So far, we started with this first module and we talked about hardware. So there we talked, about how to design a hardware accelerator for neural networks, how to evaluate different accelerators and compare them to each other, a few efficiency techniques like sparsity and low precision, and how that affects the power consumption and the area utilization even of a machine learning accelerator. And then we went a bit into microarchitecture, where we looked at the design of a processing element and what that looks like. So looking at kind of that first module, is there anything else you wanted to get out of the hardware module of this course? Is there something you feel is like missing? I don't know about that. I wanted to know about it. Or is it kind of it's done? You're experts in hardware now. You're ready to move on. So you're all experts? No? Yeah. So it's some people are saying no, some people are saying yes. So yeah. So I mean, this you know more than most people about hardware at this point, machine learning hardware. But obviously, you only become an expert when you start designing one yourself, or you kind of work with a piece of hardware and you compare it to other things in some kind of setting. So we didn't really get much of that, and unfortunately, it's hard to fit into this course just because of kind of how many design tools we need for designing hardware and the kind of the background knowledge as well. But if you do have lingering questions, or if you want to work in any kind of hardware project, feel free to follow up with me, and I can lead you in the right direction as well. But by now, you know more than most people about hardware, so that's good. So the next module is this neural networks module. And these are general techniques to make neural networks more efficient. So oftentimes we apply those techniques because we want to get a specific throughput or a specific latency out of a constrained hardware platform. But more and more I'm seeing that, you need to apply those techniques anyways, because deep learning workloads are becoming so heavy that even kind of the big data center hardware can't support that sustainably anymore. And you need to kind of apply these efficiency techniques regardless of whether you're doing it on a mobile phone or on a Tesla A100 GPU, right? Someone contacted me from a startup doing kind of these automated, what do they call them? Like phone support people. Like they want to replace those phone support by just an automated system that speaks back to you, like an AI system. And I told him, like, why are you talking to me? I build hardware and I do efficient kind of machine learning. It's like, we need that anyways, even if we're implementing our solution to the cloud, it's all kind of a dollar cost to us. We need to rent all of those AWS servers and it costs a lot of money. So making our models more efficient is kind of our #1 priority, and we need to start the team doing that. And so, so these techniques are relevant if you're deploying a model to a mobile phone, because without them, you can't deploy it to a mobile phone, but they're also super relevant if you're deploying your model to a data center, because otherwise it costs money, electricity, and sometimes it just becomes infeasible as well. So we will talk about quantization. And the main motivation for that, going back to this slide here from the hardware lecture, is that, we save a lot of energy if we operate in lower numerical precision. So you see here how, going from FP32 to int32 addition, we save about 9x in energy consumption. The same is true in multiplication, where we can save almost 18 times the energy between int8 and FP32. And finally, we also kind of scale the memory access energy linearly with the number of bits. So if we're using 4 less bits, then it's 4 times more energy efficient when you're accessing memory. By the way, when I say FP32 and int8, does everyone know what I mean by now? Yes, okay, that's good. So more benefits of quantization. I kind of touched upon the second point here, the power consumption or the energy consumption. But as I said, you also save a lot on memory, and not just the energy to bring data from memory onto your chip, but also just the memory storage. So we looked at these MCUs and how they have very small flash. By kind of quantizing your numbers to 8-bit precision from FP32, for example, you need a quarter of that storage. And so for constrained systems where you don't have enough memory, this is also really useful. Latency, obviously, when you have a more efficient circuit, you can stamp out more of it on the chip and therefore do things faster. And B, you access the memory less often because your data words are now much smaller. So this also speeds up your application if it's memory bound. And finally, silicon area, which is, again, it's always directly proportional to your power savings. So you're saving area, so you're also saving power. So you can build more of this more of these PEs on the chip, or you can just have a smaller chip and save power. So it's always a trade-off that way. Okay, so what is quantization? So I copied this from Wikipedia. So basically, quantization, it's the process of mapping input values from a large set to a small set. That large set is often continuous, so something like real numbers. So real numbers are continuous, have infinite precision. And then you're mapping it to a countable smaller set. So like int8 numbers, which has exactly 256 values that it can assume. And so how do you do that mapping? That's called quantization. And so quantization is not a new thing. So if you took any communication course or like in classical engineering courses related to communication, they talk a lot about quantization, because in communication you're sending waves, and waves have continuous values, and then you need to sample them and you need to quantize them, send them through an analog to digital converter, and deal with them in the digital domain using bits. And so quantization has been around for a long time. It's just been adapted to kind of this field of neural networks, and it's starting to mean essentially going from floating point precision to integer precision, or a large number of bits to a small number of bits. Sometimes it's floating point to floating point, or integer to integer, or fixed point to fixed point. And so that's kind of the new definition almost for us as people optimizing deep neural networks. So whenever we talk about quantization, you'll often see one of those two kind of figures. The first one is just a number line. So this is a number, here is 0, here are positive numbers, and here are negative numbers. And this is the domain that you're mapping from. Usually we denote it by R, standing for real numbers, and then to a quantized domain Q, which has a specific number of bits. In this case, it's 8 bits. and goes from minus 127 to 127. And so that mapping process from the real value numbers to the quantized numbers, that's called quantization. And you'll often see it also plotted that way, where your y-axis is the quantization function, which maps values from the x-axis onto this what looks like a step function. So all of the values kind of in this range will map to the same quantized value, even though they have different real values. So that's usually what a quantization function looks like on a 2D plot. Okay. Yes, so as I said, kind of that term quantization has been there for a long time, and it is being redefined for deep neural networks. And when you see quantization written out there, it usually means at the moment going from FP32 to int8. That's not the only quantization possible, but that's what it usually means nowadays. And that's what we'll focus on here, but like I said, there are many kinds of quantization which do not mean that. So what are we mapping, right? Like how many distinct numbers are we mapping from, and how many distinct numbers are we mapping to? Unlike the kind of the formal definition of quantization that you're going from real values, we're actually interested in going from these floating point values, right? And in FP32, you can map you have about 4 billion distinct numbers that you can represent, right? You have 32 bits. I think 8 of them are for the exponent, and some of them are for the mantissa, 23, I think, and 1 bit is for the sign. If you kind of work that out using pen and paper, you'll find that you have about 4 billion numbers that are representable in FP32. We want to go to int8, which has exactly 256 numbers that you can represent. So you're definitely kind of reducing your representational capacity of this numbering system by a lot. Like, I don't know, what is this? Like 10 orders of magnitude, something like that, or 7 orders of magnitude. So you're reducing this representational capacity by like a very large amount. So you have to be careful there. You're also reducing your range by a lot. So the largest number you can represent in FP32 is really huge. It's 10 to the power of 38. Whereas the largest number you can represent in int8 is 255 if you're using unsigned numbers. And so how is this possible? How does it work? If you go to from FP32 to int8, and you can still run a neural network and get meaningful results at the output. And the answer lies in, okay, neural networks are very tolerant to reduced precision. They have a lot of redundancy and all of these things. But it's also the way we train neural networks, the way we normalize numbers within them, you usually end up with a distribution of numbers that looks a lot like a normal distribution or a Gaussian distribution. It doesn't always look like that, and it really depends on how you train it and what optimizers you use. But typically, it looks something like that. Usually, your numerical range is quite small, and -5 to 5 is just an example. I've seen it from -0.5 to 0.5 as well. But yeah, so basically your trained parameters usually fall within that that kind of nice simple distribution with a relatively small range. So what about my inputs? So I'm talking now about parameters or trained parameters. For inputs, it's a similar story as well. You'll often hear this term, in-domain inputs or out-of-domain inputs. Usually the domain that you're operating on has some reasonable values. So, images, they're already actually usually represented in 8-bit numbers. So, you have 3 channels, RGB. Each channel has an 8-bit number representing the intensity of that color. You also have, larger bit images and smaller bit images as well. But usually your domain of natural occurring data like images or speech is quite limited in its numerical ranges. And so for those 3 reasons, quantization often works, even though you're mapping from that very large range to this very small range. Okay, so so that's kind of just an intro to what quantization is. But we really want to dive deep into what does quantization mean for neural networks. So we have a neural network here, and we want to quantize it. What should we care about? So, I mean, the first question that comes to my mind is, should we care about weights or activations? So parameters or inputs. So which one of those are we going to quantize? So that's an important question to answer. Do we use linear or nonlinear quantization? Right? And if you don't know what that means, you will by the end of this lecture. Do we use symmetric or asymmetric quantization? These are two different types of linear quantization as well. What do we do during training? Can we somehow regularize training to improve the results of a quantized model? So that's something called quantization-aware training. And where do we apply quantization? Do we apply it for training to make training more efficient, or do we apply it to inference to make inference more efficient? Usually you'll find that it's applied to inference, but there are cases where it's applied to training as well. And quantization involves simple mathematical operations like rounding and clipping and truncation. So what about those? What do those induce error? What kind of error do they induce? What is the trade-off there? And finally, what is the granularity of my quantization? Do I do it per network? Do I quantize the whole network using the same range? Or do I quantize each tensor in my network using a specific range? Or do I quantize each channel in my network using a specific range as well? So what is the granularity? So these are all questions that we'll try to answer in this lecture. And by the end, you should know all about these things. Yes, Sri. Channel. So I'm using here kind of terminology from mainly the image domain, where typically an image has 3 channels: red, green, and blue. It refers to kind of the different colors. But as you move through the neural network, you're also adding more channels. They call them feature channels. So your input tensor is 3 channels, but then usually it turns into 16, and then goes all the way up to 2K channels, 2,000 channels, and then kind of you do your classification that way. So it's basically the third dimension of a tensor. Okay, so let's start with the basics and back to our number line. So here I have a number line with some example numbers, real numbers represented here. And then I want to map it to a quantized domain. And so that is called quantization. And so what is happening here? What is the function that I'm applying to my numbers? So I have a quantized number equal something, a function, and the input is a real number. So what kind of function is this? What does it look like? Step function, yeah, that's right. So it looks like that step function that we looked at the beginning. If I want to write it out, what would it look like? The sum of step functions. Right. Oh, I see. I think that could work actually, but there's still a simpler, there's an even simpler method to write it out. And I mean, it looks something like this. So basically, I take my real number, I divide it by some number which I'll call a scale, and then I add it to a number that I call a 0 point, and then I clip the whole thing based on my range. So my range in this case is from 0 to 2 to the power of b minus 1. So if I haven't already, I don't think I've mentioned it, but b here is the number of bits that I am using in my quantized number. And so usually if you have, if you have b bits, then you can go from 0 to 2 to the power of b minus 1 numbers, right? So if I have 4 bits, I can represent numbers from 0 to 2, this is wrong, to 2 to the power of 4 minus 1, so 0 to 15. So that stands for 0, 0, 0, 0, all the way to 1, 1, 1, 1, right? And so that's my quantized range. So I need to clip if I go over that range. And then for all of the numbers, these real values, I'm dividing them by a scale factor and adding them to a 0 point. And that's general quantization from real values to quantized values. So the next question becomes, how do I find my scale and 0 point? It seems that those are essential for doing this quantization process. So can someone think of how to calculate that scale? Um, whoops. Okay. Actually, I skipped a slide. So we'll go back to the scale. But before we even talk about the scale and the 0 point, do you think this is linear or nonlinear quantization? And do you think it is symmetric or asymmetric? So who thinks it's linear and symmetric quantization? Who thinks, okay, so 1%, 2.5, 3.5, okay. Who thinks it's linear and asymmetric quantization? More people, okay. Who thinks it's nonlinear quantization? Okay, good. So, so it is kind of a trick question because this function is a nonlinear function because of this clip that I have, right? But this is the function for linear quantization, and so everything inside of that clip is a linear function. I mean, it still has a round, but this is basically what's called linear quantization. I can map from my real values to my quantized values using a function, a simple function that I can write out and compute, um, and um, and it's kind of linear. Let's call it that way. Whether it's symmetric or asymmetric depends on my 0 point. It doesn't really depend on this function. So if the 0 point is 0, that's what we call symmetric. If it's a value, then it is asymmetric. And so coming back to that scale factor, hopefully you had a bit of time to think about it now. Yes, Rashmi. Yeah, yeah, we'll get to it here, but it's a good question because I haven't really said so. um, so coming back to our scale factor, so how I compute that is, I pick a maximum and minimum value that I want to represent from my continuous real values. So as I said, you can represent up to like 4 billion numbers and 10 to the power of 38. What is the maximum value I want to represent in my quantized numbers? And usually you look at your numerical distribution. So, it looks something like this. So you pick, an Rmin and an Rmax somehow. There are different ways of choosing that. Sometimes you choose just the smallest and largest number you have. Sometimes you choose, the smallest and largest number. Take like at your like 90th quartile or something like that. So you just ignore those numbers and you clip them. Sometimes you do other algorithms, and sometimes you actually learn those values using an optimization algorithm as well. But basically now I've decided, this is the largest number that I want to represent. This is the smallest number I want to represent. And so, so to answer Rashmi's question, what I'm going to clip is any number greater than Rmax, basically. It's going to map onto the same value as my largest number, right? So that's the clipping function. And then my scale factor is simply, Rmax minus Rmin divided by the number of bits, right? So what am I doing here? I'm doing, 0.3, that's the largest number, minus negative 0.3 divided by the number of bits. Let's always use 8 bits as our example. So, it has 256 bits. I think this is supposed to be 255, but it doesn't really matter. So that's equal 0.6 divided by 255. And so that's my scale factor, right? And so now what this will do is that it will map, at least, if I plug the scale factor into the equation, now if I have the value 0.3, I will divide it by, my scale factor. So 0.3 divided by 0.6 times 255, which is equal to 127.5, but then I have a rounding function. And so what this is doing is that it's changing the range of my numbers from whatever range they have, which is Rmin to Rmax, to my new range, which is 0 to 2 to the power of b minus 1. So that's my new range, and this is my old range. I'm just creating a mapping one-to-one. I used to have an 0.3. I want to represent it using 8 bits. Now because this is the maximum value, I'm representing it by that maximum value. right? And then to make it even more general, I add the 0 point. So what is the 0 point? The 0 point is very simply, what is the value that I'm going to map my 0 to? So can someone guess what the 0 point here is? Zero. I actually have a 0 on the Q line, so it's not 0, but usually in a lot of cases it is 0, but in this case it isn't. I'm sorry, who's talking? Yeah, that's right. So in this case, that's what I chose. I mean, you can't infer it 100% from this diagram, but that's actually what I chose it to be. So now I've taken this number. You know, it looked like this. I'm rounding it down, so it's 127, and I'm adding to a 0 point, which is another 127. So my result is 255. So now the 0.3 according to the scale factor computed by this, and the 0 point chosen as, you know, the value 127, I can map this 0.3 down to 255 here if this is 8-bit quantization. Yeah, that's a great question, and it does matter. So I have one slide about that, but you will find like many papers on rounding. Okay. So is this now kind of 100% clear? Yes, Rashmi. Yeah, that's right. So basically, it all depends on your choice of where the 0 point is. In this simple example, I just mapped to an unsigned number, but you can also map to a signed number and choose your 0 point to be 0, for example. So that's also possible. And I mentioned clipping quickly in the middle, but basically, clipping is what happens, you know, to any number that is larger than your 2 to the power of b minus 1. So if we apply the same equation on 0.35 here, because it's outside of our range, it's bigger than R max, then this clip function will clip it down to 2 to the power of b minus 1, which is 255. So you'll see that those two numbers are mapping to this one here, right? Okay, yep. Yeah, exactly. Yeah. All right. Okay. So that's the quantization process. So what about dequantization? How do I go back from my quantized domain into real valued numbers? And so the equation here looks even simpler. So it is kind of the inverse of this one. So the real number is equal to the scale times the quantized number minus z. And so if you rearrange this equation and get rid of some of those nonlinearities, then you'll come up with this. And I think that's why it's called linear quantization, because this mapping is obviously a linear one. And so what happened here? Like the output numbers have now lost some information, right? So I did this mapping. Some numbers aliased onto the same number, like here and here. Some numbers were clipped. Some numbers were outside of my range. Some numbers were rounded. And so I'm getting some error. So the quantization error is basically the main reason quantization doesn't work perfectly, and that's why, you know, that's what we're trying to minimize as people doing quantization, or we're trying to make our neural network more resilient to those quantization errors. So what are they? There are two sources of errors from this kind of quantization. First one is called clipping error. So any number that I clip introduces an error, obviously, because it's no longer mapped to my quantized range. It's outside of the range, and I have to clip it down to the maximum value. It saturates. So that's kind of denoted here. You see this 0.35. I mapped it to a number. When I mapped it back, it was to a much smaller number. So this is a clipping error. And then there's also rounding error. So here I see that number minus 0.22. It's mapped to that number. When I map it back, there is a difference between the original number and what the dequantized equivalent looks like. So that's called the rounding error, and it is bound by your scale factor, basically. I also want you to think of the scale factor as your step. So this scale factor is the size of your step. So if anything in your real valued numbers up here, this is, if you get any number and add this to it, then it would correspond to a +1 in your quantized range, if that makes sense. So this is your step in the real valued domain that corresponds to one step in the quantized domain. And so the rounding error is usually from minus half of that step to half of that scale factor. Okay, so now I'm designing this quantization system. So how do I make this rounding error smaller? What do you think? So here's the equation again for the rounding error. Do I increase Rmax? So I get to choose the range that I'm quantizing in. So so how can I change that range to make the rounding error smaller? Yeah. Right. Yeah. So Sam, right? Sam said increase our min and decrease our max to have a smaller range. So a smaller range means a smaller step size, and the equation just says, if the step size or your scale factor is smaller, then your error is smaller because you can represent numbers at a finer granularity. Your step becomes much smaller, and so you get less rounding error. And that's correct. So so that's what you do to decrease your rounding error. But what is kind of the bad side effect of this? If I decrease my range, then all of a sudden now, I'm pushing this Rmax in this direction, I'm pushing this Rmin to this direction, and so that increases my clipping error. So usually there's a trade-off between rounding error and clipping error, and you have to be careful when you're choosing that. Okay. Okay, so Harish, right? So Harish asked about rounding. And so actually when we were working on our accelerator back at Intel, we used to just clip the number. So basically we used to always round down because that's the cheapest thing to do in hardware. You don't look at your kind of remainder, you don't do anything with it, you just get rid of it. And that works really bad. So we found that we dropped a lot of accuracy. And you'll see in this table here, which is from a paper kind of investigating different rounding schemes, your accuracy drops to 0.1. Basically, your model becomes broken, something. But it really affects your accuracy, basically. And so, so this is from a paper where they do quantization down to 4 bits, so a very small number. And when they use the floor function for rounding, you lost all of your accuracy. When you use the ceiling function for rounding, you lost all of your accuracy as well. Basically, what these functions do is that they introduce a bias, and when your numerical range is 0 to 16, this introduces a very large bias in your network, and it breaks everything. A very good rounding function and a safe bet is round to nearest, which is typically how you would round a number. You just you round it up if it's closer to that up number. You round it down if it's closer to that down number. So that gives you an accuracy of 52%. But then the people in that paper found that if you round randomly up or down, you also get close to that round to nearest number. So every time you need to round, you just randomly either round up or round down. So that's called stochastic rounding. But obviously it has a large kind of standard deviation because it's random. Like sometimes you get it right, sometimes you get it wrong. But the best result from this stochastic rounding is actually way better than round to nearest. The rest of this paper, and if you're interested, it's down there in the source, goes through a way of doing adaptive routing and rounding and learning kind of the rounding scheme as you're doing training. And so that's a really cool paper. And by the way, I'm talking about this rounding function, right? Yeah, good question. I don't remember exactly what they did there. but it has some overhead, obviously. So going to that paper will give you the answer. Okay. Okay, so far kind of we covered some of those points. We talked about, linear quantization, how to go and quantize, how to dequantize. We talked about both symmetric and asymmetric, and that it depends on basically the 0 point. And finally, we talked about rounding and clipping error and also different kinds of rounding. Yeah. Yeah, so logarithmic rounding is definitely very useful, and some people use it. Man, I should have added a slide on it, but I don't have one. It will be in the book, though. So if you go through your readings, you'll read more about logarithmic rounding as well. So logarithmic rounding is basically that function has a log in it, and it's nice because if you look at the distribution, you actually have a lot of numbers here. So linear rounding, or not rounding, linear quantization basically will assign numbers equally along that number line. So, you have a value here, a value here, a value here, a value here, and so on. So even though you have so many numbers here and you probably want better resolution here, you still have the same kind of scale factor. So it's a single scale factor throughout. Logarithmic quantization changes that scale factor based on where you are. So usually it works well for something that looks like this, right? Where you need a lot of resolution here and then not so much here. So it gets kind of more spaced out. And then there's something called nonlinear rounding, which we'll also talk about, which is a general way of doing this as well. Okay, let's move on. So linear quantization. So that's what we've been discussing so far. Now let's apply this linear quantization on a matrix multiplication. So we have, weight matrix W, activation matrix X, and we want a result Y out from multiplying those two matrices. So, so if I want to do that matrix multiplication now in the quantized domain, Y becomes approximately equal to this function. And so how did I get this function? I basically plugged in that quantization equation I have in the corner into W and X. So now I have a scale factor for W. I have the quantized version of W, so it's all quantized to, let's say, 8-bit. And I have a 0 point for W, right? The same is true for the activations. So I computed, a scale factor and the 0 point, and I quantized my X tensor. Does that make sense? So now that's quantized matrix multiplication. Makes sense? Yes. Okay. And so if my linear quantization scheme is symmetric, then all of my 0 points are 0. And so it simply becomes, I have the two scale factors multiplied by each other, and then the normal matrix multiplication, but now it's with quantized numbers. So now I get to do kind of quantized arithmetic here. So this is 8-bit arithmetic. And then I just have these scale factors that I multiply with. And so James, to your earlier question, when you asked kind of what happens to the numbers, where are they? And so the Y value doesn't change here, right? Because I am multiplying by those scale factors, but just the product of W and X now has a different range. It goes from, for example, to 0 to 255. But I still have those scale factors here. So Y is approximately the same Y in my floating point multiplication, right? It's just, if I multiply out the scale factor, you get approximately the same result. Obviously, it's not exactly the same result because I have a quantization error, but I need to maintain the same arithmetic throughout my network. And so I still have those numbers here that I need to multiply with. And so what happens in the asymmetric case? So here in the symmetric case, the overhead is quite small because I have this just one constant scalar value that I need to multiply with all the numbers after they come out of the quantized multiplication. So this scale factor is here. But for asymmetric, I basically need to multiply out this equation because my 0 values are no longer 0. So it looks something like this, right? So it's no longer just matrix multiplication. It's matrix multiplication plus something else and plus something else. And the colors are confusing, so I color it in a different way to show what numbers are actually constant scalars versus what numbers are matrices and change. And so you'll find that the first term is the same as my symmetric quantization. So it's just a scaled matrix multiplication, basically. You can still do it in the quantized domain. And then there are two numbers which are basically all constants. And what I do with those typically is that I fold these into my bias addition. So usually, in a linear layer or something, you have matrix multiplication plus bias, or in a convolution layer, the same thing, you have a convolution plus bias. And so these values are just a constant scalar value that you're adding to all of your numbers. So I just fold it into the bias. Yeah. WQ, oh, that's a great question, Harish. So Harish is saying, WQ is a matrix, it's not a constant value. And that's true. So it's not a scalar. So I said scalar and that was wrong. Harish corrected me. That's a good point. But it is constant during inference. So that's kind of one implicit thing that's one implicit assumption I've been making so far as well, is that we're doing this during inference. After we trained our model and our weights are a constant thing that don't change at all. And so all of these numbers become constant now, which, like I said, I can fold into the bias addition. Whereas I have this extra term, which I cannot fold because I don't know the x value beforehand. So I need to do this extra computation, and this is called, quantization overhead. So you don't just get to do your math in lower precision arithmetic. You also have this overhead if you want to support asymmetric quantization that you need to compute online. And it's roughly equal to the overhead of adding one channel to your tensor. So if you have many channels, then it becomes a small overhead. If you have very few channels, it's a large chunk of your computation. So how do I get rid of this online overhead of asymmetric quantization? What is one simple way of just forgetting about it, not having that extra overhead? What do you think? So yeah, one thing I can do is I can make that 0 point equal to 0. So usually actually what people do is that they use asymmetric quantization for the activations and your inputs, but they use symmetric quantization for weights. So setting that ZW to 0 means that my activations can still have asymmetric quantization, and that works well for activations actually. Especially with kind of skewed nonlinear functions like ReLU, which really skews your activations to be on one side of the number line. Whereas weights are usually centered around 0, or we try to do that during training. So usually symmetric quantization works well for weights, and it also simplifies my equation here. And so I don't have any real overhead from quantization in this case. Does that make sense? Okay. And so I mentioned, the scale value, the 0 point. What is the granularity of choosing, the scale value and the 0 point? You can choose one scale value for your entire network. That's possible, but usually that's not a good choice because you have very different numbers, and yeah, so you end up clipping your clipping error ends up being too large in some places, and your rounding error ends up being too large in other places. And so the different granularities you can do this at is per network, per tensor, so per weight tensor, or per channel in that weight tensor. So you break down that weight tensor into different pieces, and you choose a range and a 0 point for each one of those pieces. And in this case, I'm just showing channels. So here, these 3 channels, RGB, each one of them I'm going to compute Rmax and Rmin, and I'm going to select a 0 point based on the numbers in that volume. You can also go to different smaller granularities, but these are the most common ones. In current hardware, you'll find that most of it, that supports quantization will support per tensor quantization because it's kind of simpler and easier to think about. But increasingly, people are moving towards per channel because it has kind of the smallest effect on overall accuracy, typically. Yeah. Okay. So we covered a bit more from that list. So we talked about weights and activations and went through that matrix multiplication example where we do quantization. And we talked a bit more about symmetric and asymmetric quantization in that context as well. Whoops. Oh, there's a question in the chat. Kim is asking, when is asymmetric quantization useful? So I gave one example of that. So it's useful when you have a skewed numerical distribution, like the one that comes out of ReLU, which is all positive numbers, basically. So asymmetric quantization is useful there. Yeah, and it really just depends on your numbers. And asymmetric quantization is more general and more adaptable to your kind of a numerical distribution. And so usually it gives you the most flexibility, whereas you take some of that flexibility away when you go to symmetric quantization. Okay, and now let's try to cover some more of those things that we care about related to quantization. Okay, so yes, implicitly, so far we have been talking about post-training quantization. So I've trained my model. I want to deploy it on a phone, for example. And so to do that and to have it run efficiently, I take that trained model, I try to change all of those weights to be int8 numbers instead of floating point 32. And that's after training. And then also the activations as they're coming in, I'm changing them from FP32 to int8 as well. And so, I do the neural network training, and then I move on to this post-training quantization. So weights, the weights are frozen and pre-computed, but what about activations, right? So, I mean, I have a training set, which I've seen before, but what about, my test set? If I deploy this model to the wild, like what happens to, how do I find the quantization range of my activations or my inputs for that matter, right? So how do I compute that? So for the weights, it's easy, right? I have all the numbers, they're already pre-trained, they're already there. But what about inputs? What's an approximate way of kind of finding the ranges of the inputs? How do I choose the scale in 0 point? Yeah. So when he said based on the task, because each domain has kind of a specific range, and that makes perfect sense to me. But what about, let's say I'm looking only at black and white images in one application, and in the other one I'm looking at color images. So or I'm looking at images of cats, and they all have a specific range of colors, for example. So yeah, James. So the mean of what? And standard deviation of what? Based on your training set. Okay, so James said, let's just do it based on the training set. And that's usually what people do. So they either do it based on the training set or based on a representative test or validation set, right? It doesn't have to be the training set. Usually, actually, we do it on a validation set that wasn't used for training. But we just take a representative mini batch. We run it through the network. We store all of the intermediate activations. We compute R max and R min, compute the scale factor, we compute the 0 point. And so we do it experimentally based on that single mini batch and hope that it extrapolates well to other inputs that we see when this application is running. So you can take as many mini batches as you want, but usually a mini batch, like you should take a representative mini batch. Let me put it that way, or a representative batch of data. So doing it on the entire training set may be a bit too much. So you get diminishing returns basically. Okay. Okay, so that's post-training quantization. So, the weights, we have them, we compute the R max and R min. And like I said, there are different ways of doing that, and I should have had a slide about it, but I don't. But basically, we usually we usually take like 90th quantiles or something. So we basically exclude outliers and then choose our R max and R min to cover most of our numbers. So 90% of our numbers or 95% or something like that. So that's post-training quantization. There's also something called quantization-aware training, and so that's what we will talk about next. Just so so as you know, post-training quantization, you already trained your network without any awareness of the fact that you're going to quantize it afterwards. But in quantization-aware training, during training, we add something called simulated quantization. And why do we do that? We do that basically to make the neural network more robust to quantization. Basically, you're essentially adding your quantization error through the network to your loss. And so through backpropagation, you should nudge your weights in the right direction to compensate for that quantization error, if that makes sense. And so here is a simple graph of, training a convolutional layer followed by a bias addition, and then a ReLU 6 activation function. And so to simulate quantization during training, we do something that's actually really simple. We don't want to change our GPUs to support integer math, although they do now. But we don't want to change our training in any way. So we add these quant nodes here. And what they're usually called is fake quantization nodes. And what that means is that we basically take the numbers, we quantize them, and then we dequantize them, and then we do the operation as normal before. So that's kind of the minimal change in my training graph to be able to simulate the effects of quantization. So everything here is still FP32. All of the operations and everything, I didn't change them at all. But all I did is, my input here is float, and my output here is float as well. But what I did is that I quantized and then I dequantized. So what effect does that have? So for example, if I had this number 0.35 in my previous example, I quantize it, it goes to 255, and then I dequantize it, it goes to 0.3 exactly. So basically, I've introduced that quantization error between those two numbers, right? Error quant. And so now I'm simulating the effects of quantization without having to change my intermediate computations in any way. So I'm quantizing the numbers, the output is still float. It still looks a lot like the input number. I don't change the math. I don't have to add these extra biases or compute this running sum that I showed in the overhead of linear quantization. But all I do is I quantize, I dequantize, and then that gives me most of what quantization actually does to your numbers, right? The other benefit of this is that all of my numbers are still floating points. And so in the backward pass, I can add very small numbers to it, meaning that I can train effectively as well. So basically in the forward pass, I apply this quantization function to all of my inputs. But in the backward pass, we actually use something called a straight-through estimator. And the straight-through estimator is nothing. It basically says the gradient of this function is 1. Because I can't really compute the gradient of this. It's 0 here and undefined here, 0 here and undefined here, 0 here and undefined here. So it's not meaningful. So instead, I just say, okay, my gradient is 1 everywhere, and this will work. And then we try it, and it works, and we're all happy. But that's basically what straight-through estimator means. We use it for a lot of quantization work. So forward pass, we do the actual thing. Backward pass, we just propagate the gradients to make sure the training works. Okay, so now we covered quantization-aware training as well. Yeah. Yeah. Yeah, so that's a good question. So in what context do we want to do simulated quantization during training? Basically, it's in the case where I want to perform post-training quantization and I'm losing too much accuracy. So I say, okay, instead of training my neural network without any awareness of the fact that it will be quantized later, I'm going to tell it you're going to be quantized later. And what does that have effect concretely on the training? It basically adds that quantization loss, aggregated from all of these errors of doing quantization. It gets added to my final loss of the network because it changes my final number in some wrong direction. And then through backpropagation, that error should nudge the weights in my network to compensate for that quantization loss as well, if that makes sense. So basically, if you're doing something during training, it helps, it allows the training process to compensate for that thing that you're doing during training, which in this case is quantization. So 3. Yeah, that's a great point. So basically, you want to simulate whatever quantization you'll do post-training during training. So it's the same numerical precision and numerical format. Yep. Yeah, yeah, there are no drawbacks. Usually, it's only as effective as kind of adding half or 1% to your accuracy. It doesn't kind of, it's not the difference between 0 and 50% like we saw before with rounding. It gives you a marginal improvement with a marginal increase in GPU runtime or whatever training chip runtime as well. So there's no reason not to do it. It's just a bit of extra work, a bit of extra runtime. So okay. Now we're missing, we've been talking about linear quantization all that time. Talked about how to do it, how to quantize, dequantize, do it during training, simulated during training, do it on a matrix multiplication and what the overhead is and all of that. But we haven't really talked about nonlinear quantization at all, except due to Harish's question about logarithmic quantization. And so what is nonlinear quantization? And so I think it's summarized well in this picture, where you have a weird numerical distribution. And you can see this during training. I've seen it in some cases, where you have kind of a two-peak distribution. And what linear quantization will give you are those x's here. You will choose kind of a discrete set of values that are equally spaced by the value of your scale factor, if you remember. And they cover a specific range that you define, right? So in this case, this is the range that I chose because maybe some numbers are in that range here. And so even though most of my numbers live here and here, this linear quantization, what it gives me is a numbering format in which numbers are equally spaced and do not really take into account your input distribution anyway. What nonlinear quantization gives you is a numbering system that exactly or approximately matches your input distribution. So in this case, if I were to kind of draw by hand where I want to represent numbers, maybe I'll put these red dots here, right? Okay, I will want to have a number here to distinguish between this one, and then most of my numbers I will cluster them somewhere here, close to that peak, and somewhere here close to that peak, because that's where most of my numbers live, and so these are the numbers that I actually care about, right? So that's nonlinear quantization. And what the technique that people use for nonlinear quantization is usually a clustering algorithm. So until now, people use something like k-means clustering to do that. Who knows what k-means clustering is? A few people. So yeah, I mean, it's an algorithm where when you have some numbers, you're basically trying to divide those numbers up into different clusters. So we start by saying, okay, I want to have 3 clusters, those 3 colors here. All the numbers are in the blue cluster, but then as my algorithm kind of operates, we're changing which cluster each set of numbers belong to, and we end up with RGB clusters here. So 3 clusters, 3 numbers associated with each cluster. And so what does this mean? So if I have a set of weights like this one, I'm choosing a specific number to represent each group of numbers in that weight. Here in that weight matrix, it's represented by the color. So what I actually need to store now is not the actual number. So, 2.09, 1.92, 1.87, 2.12. I only store the index here. So these blue numbers are all stored with index. Okay, this belongs to my cluster 1, 1, 1, 1, 1, right? And so what number represents that cluster? It's usually kind of the average of all of these numbers. And in k-means terminology, it's the centroid of this cluster. So usually the average of the numbers that belong to that cluster. So if I have k clusters in this case, I need binary logarithm of k bits to represent those centroids. So basically, let's say I have 8 clusters, then I would need log2 8, so 3 bits. 3 bits, yeah, 3 bits to represent these cluster indices. So the number of bits to represent my weights now goes down from, it used to be FP32 all the way down to 3 bits. So usually you can get really good compression with nonlinear quantization. And so what do these 3 bits represent? They represent an index. So for example, 101. So that represents, this number corresponds to cluster 5, and it will be all represented using some kind of average or centroid for my k-mean cluster. So 3.189, for example. So any arbitrary still. So still the number is FP32. Still, the index is a very small bit width number, so 3 bits. This number is high accuracy though, like it's high precision. It has a lot of decimal points. And so, yeah, so that's what it would look like for a 2D matrix. So you'll just, need to store the cluster index. In this case, it's a 2-bit cluster index. So, okay, so I mean, we talked about quantization and dequantization functions before. So my quantization function here is k-means clustering algorithm. So it's definitely a nonlinear function. It performs this algorithm and it finds this this table of indices to floating point numbers. But what is my dequantization function? So yeah, that's right. So that's what we do. But still, what is the function to do dequantization? So each number now is represented by an index, right? So how do I get the number? So it's basically it's a lookup table, right? So I have each number is represented by an index, like we saw here. So 3, 0, 1, and so on. And so before I do the computation, I just look up that index in something that's usually called a codebook. If you read any paper, it will be called a quantization codebook. And so it will have a specific value corresponding to the centroid of that cluster that's representing my number. And so now if I have an FP32 operation like this one, this is matrix multiplication, for example, or convolution, I have FP32 inputs and FP32 weights and FP32 outputs. In nonlinear quantization, all I do is that I encode my weights using this codebook, and then before I do the computation, I look it up in the codebook and I do the computation. So this doesn't actually affect my runtime. In fact, it might slow down my runtime a little bit. But what it really benefits, where it really benefits me is I have a much smaller model size. So my parameters become very small, and usually at a very small accuracy loss as well. So that's why we focused on linear quantization. Whenever we're talking about hardware, we really care about linear quantization because you can do this reduced precision arithmetic, like 8-bit matrix multiplication and so on. In this case, we're not doing that. We just care about the storage, the memory footprint of my model, and that's the real benefit of nonlinear quantization. So it could be the difference of using a DRAM chip to store your model or storing that whole thing in on-chip memory. And you can typically store the code book in on-chip as well, on-chip memory, because it's usually very small. And so, it really benefits you definitely in memory-bound applications, or in a chip that doesn't have external memory or a large memory, where you don't really care about runtime, because you still have to do your computations in high precision. Okay, so we covered most of that now. For training part, I don't have a slide. Go read the IBM paper on it. It's one of the recommended readings this week. But basically, you can also just do training in lower precision to save energy and speed up training itself. So we've talked about inference so far, but you can also do it in training to make that faster or more power efficient. And so someone at this point is thinking, quantization is boring. You just use smaller numbers, save energy, so what, right? And so I just have this one example, which is my last slide actually, about something called product quantization, which is a really interesting way of thinking about quantization as well. So if you think quantization is boring so far, check this one out. So basically here, we're not quantizing each number. Instead, we're quantizing each group of numbers into something called a prototype. So again, if you're interested, read the paper, but I'll try to give you a quick rundown of what's happening here. Let's say we have a vector A and a vector B that we want to multiply. What I do is that through a clustering algorithm, again, like k-means clustering, I choose a shape that's closest to my piece of vector A. So in this case, vector A, it looks like a pyramid here or a triangle. I look at a bunch of prototypes that I've already learned offline. And I say, oh, this looks a lot like this one. So I'm going to approximate this group of numbers. So this here is like, let's say 16 numbers. It starts with 0, 1, 2, 5, 8, 11, and so on. So the group of numbers have this pattern that's increasing and then decreasing. So I'll represent this group of numbers using this shape that I learned offline, which also looks very similar. And so what I'm doing here is that I'm doing quantization not on the single number granularity, but on a vector granularity. So I'm replacing this group of numbers by this prototype. And then this other part looks like this, like a semicircle. So, it looks a bit like this one, so this is what I'll represent it with, and so on. And so now I encode this whole data vector. Let's say it has, I don't know, each prototype has 16 numbers. So the whole thing has 48 numbers. I'm representing it now by these 3 numbers and exactly 6 bits, which correspond to the index of my prototype. And then I want to multiply it by this query vector B, or what's called the query vector B here, and do a dot product basically. And so what I do is, again, I match those with my prototypes here, and I can store all of the multiplications, the pairwise multiplications of those prototypes offline in a table. So I say, if I have this prototype, this red one, multiplied by this double pyramid thing or double, ridge thing here, then the number that I get out is 3. And then I look up that number, I put it here. And then here, if I multiply this prototype with this prototype, the number should be 1, and so on. And so to compute that whole dot product, I've now approximated my vectors using these prototypes. I've already pre-computed all of the values of doing a dot product between those prototypes offline, put it in a huge table, and then all I need to do is just add those pre-computed numbers, and I get a result. So this is from an interesting paper published last year called Multiplying Matrices Without Multiplying. And so this is an example of where people are taking quantization, not just to a single number scale, but on a vector or tensor scale as well. I thought it was quite interesting. So yeah, and hopefully now you think quantization is also a bit cooler than just using fewer bits for your number. Further reading, it's also in the schedule, and that is all I have. Thank you.